Good morning. My name is Derek Pizarro. I'm a senior product manager with AST Environmental. Thank you for joining us. This is part of the RPI Group webinar series for winter 2020. Thank you for joining us wherever you are today, if it's morning or afternoon. Today's presentation is going to be focusing on BOSS 200. Our presentation today is drilling down on the trap and treat approach, part 2, petroleum hydrocarbon remediation, focusing specifically on BOSS 200. If you have questions during this webinar, please utilize the question or the chat windows in the GoToMeeting. They should be there in your control panel. Bill Brab, one of our other remediation geologists, is monitoring those, and we will bring those up at the end of the webinar and go through as many of those as we can. If we don't get through some of those, in the interest of time, we will reach out to each individual to address those questions. So here's a brief snapshot of what's left for the 2020 webinar series. Here we are today with the BOSS 200 presentation. Next week, we're going to have a after the holiday when we come back, we're going to have a two-part series on bedrock characterization and bedrock injection. This is the first time we've broken the bedrock component of our presentations and technologies into two separate webinars. But we believe it's important because these are very unique sites. These are very unique technologies, both from an injection and a characterization standpoint. So if this is fractured bedrock is something that you do on a regular basis, on an irregular basis, or you'd like to learn more about it, I encourage you to sign up for either of those two. And then we'll wrap up on December 17th with a pre-drill methodology presentation. During this webinar or for any of the subsequent webinars, it's never too late to join. If there's a colleague sitting, well, probably not sitting next to you right now in this COVID climate, but if there's a colleague you've been talking to, they can email Bob at trapandtreat.com and they can get them registered for these webinars, both today and future ones. So let's start with a brief overview of the RPI group, just to give everyone a little better understanding. I'm sure there's people on this webinar that are familiar with us, that some have some familiarity, and maybe some of you have zero familiarity with RPI, AST, or our installer network. This tripod here is really the best functioning group that we've got. It's fantastic. We break this out for a number of reasons. It makes this process unique. So I'll describe this a little bit here. This all starts with Remediation products out in Golden, Colorado. They developed the technologies we're talking about today that we talked about last week. My colleague Mike Mazzarese talked about chlorinated solvent remediation. Here today we're going to focus on petroleum hydrocarbons, but the technologies that we discuss to treat these type of sites were all developed by Remediation products. They also operate our project support laboratory. That's a pro bono laboratory for our clients and prospective clients. We'll talk about that a little bit more in subsequent slides. The second piece of this is us, AST Environmental. We conduct a lot of the project assessment and design. So if you bring a site to the RPI group, both RPI and AST will be involved in the total process, whether AST is doing the installation or an authorized installer is doing it. These other two entities of this tripod will be involved. We also do a lot of the QA/QC for both your work, our project support laboratories work, and the reason that this network exists is really to manage and control that quality. We want to make sure that whatever we're putting forth as a design for our clients, that this is the best possible approach to their site. And then the third component of this is our authorized installer network. These are all vetted companies. They've been trained by both AST and RPI. They've got the right equipment, which is necessary for these slurries that we're dealing with. We'll talk about that in subsequent slides. And we've trained their personnel. So they've got experience with the equipment. The technology allows us to appropriately inject these in the subsurface and also make adjustments on the fly. Obviously, field conditions can throw you a lot of curveballs. So it's good to be able to know how to adapt and adjust while you're in the field. In terms of our footprint, we are global. So RPI, AST, we will service your projects for the group wherever they are. It was really cool. Mike Mazzarese, one of my colleagues, just wrapped up a project in Australia. So We've got good reach wherever you are. And if you bring a site to us, we've got an installer that can help you with it, no matter where you're located in the world. So here's kind of our roadmap for today. I'm going to do a fairly deep dive on activated carbon and the treatment mechanism associated with it in BOSS 200. We'll also touch on the RDC process. We know that's extremely important. It's been talked about a lot here in 2020 by both AST, RPI. ITRC released a guidance document earlier this year, so it got some notoriety there as well. And then we'll talk about implementation of these products. Again, these are slurries, so this isn't your standard equipment or injection approach from either a design or equipment standpoint. And then we'll show you a couple of project summaries, some case studies, show you how these work in the field. So let's start by talking about applications. Again, here today, this is petroleum hydrocarbons. So we'll focus on that, but these do work on CVOCs and other applications as well. Some of the equipment we're talking about here today could be used for other contaminants of concern, say heavy metals or other applications. If that's something you have, you can reach out to us as well. But today we're going to focus on petroleum hydrocarbons. These are slurries, and using a slurry can present a number of challenges in the field. It certainly requires, as I mentioned, specific equipment, techniques, definitely different designs than a lot of typical or conventional products use out there. But that doesn't mean you're limited from using these at a multitude of different sites. Depending on what you're dealing with, if this is a distal plume or source area treatment, we can come up with a design that fits that. Geology is not going to limit you, whether these are in clays, sands, gravels, till, bedrock, weathered bedrock, transition zones. There's a way to come up with a design to achieve not just both access, but distribution in the subsurface. And as we'll talk about coming up, distribution and contact. You know, we like to say that remediation is a contact sport. That's one of the most important aspects of any technology. And certainly if you don't handle a slurry properly or install it properly in the subsurface, you could run into contact issues. So we will touch on that as well. We also have been involved in a number of sites using combined remedies. I know that's a popular buzzword these days, but I think many of us on this webinar here today would agree that as practitioners, we've been doing these type of approaches for a long time. We just didn't really have a term coined until more recently. So these do fit well. There may be some additional constraints we'd want to address if you're doing ISCO or ISCR adjacent to or before and after an application of one of these technologies. So we would address that with you on a case-by-case basis. So let's start with the trap and treat concept. I want to focus on the activated carbon component here because people that have some familiarity or maybe a new familiarity with our group associate us with activated carbon, and rightly so. That's all these products are based upon an activated carbon platform. It's a very powerful tool to use in the subsurface, but if you don't plan for its use or use it appropriately, it can also create issues. And by that, I mean, if you don't have a treatment mechanism associated with an activated carbon platform, you could run into issues. You could concentrate plumes. You might deal with desorption. As an overarching comment, at this juncture, you will never see an RPI group design an installer using these type of products for, say, PFAS, PFOA. We believe strongly that if we don't have a treatment mechanism associated with an activated carbon platform, that we won't install it in the subsurface because of the downsides to doing so. But getting back to the activated carbon itself, if you haven't used this, again, it's a really powerful tool. It immediately decreases groundwater mass. So we're talking about removing the dissolve phase from your site. Again, depending on how much activated carbon you put into the subsurface, you may get all of that immediately. If you have a heavily impacted site, you may start this continual process of desorption and transport through the groundwater column onto the activated carbon. And that's really why this tool is so powerful, especially when we're talking about petroleum hydrocarbons. Because this is activated carbon coupled with a treatment technology, and it is biological, there may be designs where we plan for, say, applying a little less product and understanding that we're going to get long-term degradation. But we know that's going to occur, so we can plan for it. And we'll discuss that in subsequent slides. In terms of the activated carbon itself, again, it's been used ex situ a lot in treatment systems, both potable and non-potable water treatment. And again, activated carbon by itself works immediately. As soon as those contaminants pass through the system, they'll be absorbed onto the surface. And in our case, we can begin treatment immediately. I'm not going to touch on BOSS 100 or CAT 100 today. Again, we're going to focus on BOSS 200. Decided to put this picture in here of our fearless leader, Dwayne Guilfoyle, taking a BOSS 100 shipment recently in Arkansas. You can see there the BOSS 100 is in drums. The reason I included this is BOSS 200's packaging is different than BOSS 100. So if you are going to bring BOSS 200 onto a site, you're typically going to see this in 50-pound bags palletized. But be it known that if you're working with one of our other technologies, there's other packaging that is involved with it. So why activated carbon? Again, this powerful tool really functions because of the type of activated carbon that RPI has selected specifically for each application. Here in the case of BOSS 200, powdered activated carbon, it's food grade, it's derived from coal as a source. And we get asked a lot, could I, I've heard from other presentations that using activated carbon is a good tool, and I agree with that, insofar as that it's good at absorbing contaminants. Depending on the pore structure, the source of the carbon, you may have very different rates of absorption and performance. But then what are you doing in the future? What are we going to see? You've sequestered a contaminant that may work very well for some sites, but honestly, you're not treating it. And that's the goal of a trap and treat approach, because that's what most of us, I believe, want to do. We want to treat the contaminant in situ. And so when we look at selecting an activated carbon for BOSS 200, BOSS 100, CAT 100, obviously we're selecting activated carbons with very high isotherms, very high absorption capacities. Other activated carbon products in the marketplace, they like to talk about a cost basis, typically by volume. I would encourage you to look at comparisons in that realm on a weight basis. And even within that weight basis, what is the value you're getting out of the specific isotherms associated with the parent material of that activated carbon? Again, we're going to use coal-based activated carbon because of its high absorption isotherms. I like this picture here on the right. We're looking at 5 grams of AC, having a surface area of a football field. Again, this just goes back to the powerful tool that this product is and the advantages it provides you in situ from absorption standpoint. And as one other note, as much as I think we'd like to use regenerated activated carbon from a sustainability standpoint, it's just not something we can do when dealing with groundwater criteria levels. Typically regenerated activated carbon is high in heavy metals. You also don't know where that was used prior, which can be very problematic as well. So all these products we're dealing with here today are virgin activated carbon. So let's focus a little bit more on the power of activated carbon. When we first talk about a site with you, our clients, prospective clients, you're going to hear AST, RPI, our installers ask for speciated data. And the reason we do that is a lot for absorption capacity, but it's also for absorption competition. When you go through these designs, you have to look at both a carbon absorption capacity, you have to look for a treatment capacity, TEAs, you have to look for this balance of what makes most sense to achieve efficient, good treatment in the subsurface. And I like this example here from our laboratory, from RPI's lab, where they're comparing the absorption capacity of benzene and ethyl benzene. And you can see even at 10 ppm, there's a significant difference, an order of magnitude, in the capacity for those two contaminants on that same activated carbon platform. They're exactly the same size. So I think this is a nice example of why we stress speciated data, why when we go through the RDC process that we talk about deriving speciated data, going out on site and getting soil, getting groundwater, to come up with this data set that allows us to accurately calculate what constraints we need from a design standpoint to select the right amount of product and where to put it at your site. So a little bit about the BOSS 200. We talked about the activated carbon component, but let's focus on the treatment component, because as I've said, that's the most important part of this product. That's what stands apart from conventional activated carbons in the marketplace. Here today, we're talking about the activated carbon component, but the treatment mechanism associated with it is a facultative blend of bacteria that RPI has developed. And this was done by harvesting native bacteria at various sites around the country over a number of months and years, and taking it into a performance laboratory and selecting the highest degraders associated with those samples, and then selecting them and culturing them into the blend we use today. In addition to the activated carbon and the facultative bacteria, we put in micro and macronutrients, primarily nitrate and sulfate for terminal electron acceptors. And this, again, comes back to the data sets, the speciated data we talked about a few minutes ago. We're not just concerned about absorption capacity, but we're talking about feeding this system that's going to continue to function for long periods of time in the subsurface. A lot of our applications with BOSS 200 could be done in one step, but there's also sites where it makes sense to do it in 2 steps, or maybe 1 or 2 steps plus a TEA bump, as a 3rd or 4th step. What are we dealing with at your site from a contaminant standpoint, a concentration standpoint? That all goes into utilizing the power of BOSS 200 here, and it becomes the key to efficiency, is knowing our constraints, evaluating the components of the BOSS 200 and how we can best apply them and design for them in situ. A little bit more recently, we developed BOSS 200 Enhanced, and really what we're talking about here is optimizing the product for sites with LNAPL. That's not to say that the standard BOSS 200 wouldn't work on some LNAPL sites, but we know with LNAPL we're going to chew through terminal electron acceptors a lot quicker. We know in a lot of cases we could not possibly, just from a physical standpoint, put in enough activated carbon into the subsurface to absorb all that LNAPL at once to get that transport and degradation in a short time frame. So the BOSS 200 Enhanced allows this system to function for a very long time if necessary in situ when you're dealing with high concentrations of contaminants or LNAPL level, percent level LNAPL concentrations. So this slide here, this is gasoline bench data from RPI's lab, and I'm bringing this in here because this is a really nice example of showing that we're not just absorbing contaminant, we're treating it. Because we can talk about this is the process that we're doing every day, which we do, but we also want to show to you, our clients, we also want to show to regulators, responsible parties, that we're not just absorbing this in the subsurface. Because if you just look at groundwater concentrations post-installation, you would believe that we absorb this onto the activated carbon and we clean up the site, but that's not the case. You have to actually degrade it. So here we're talking about a 500 milligram per liter spike of gasoline. You could see the 3-day concentration equilibrium, and that percent reduction is absorption only. That's what we're seeing in the aliquot, the spiked aliquot, and that looks good. So if you look at your site and you're like, okay, I've absorbed 80, 95% of my contamination, things look good. Well, how do you know you actually treated it? So RPI has a proprietary process to strip the contaminants that are absorbed to the activated carbon, and we can evaluate what we're actually getting for mass reduction. And that's what we see in the final 2 columns here at 30 and 120 days. We're actually looking at what has been degraded by the bacteria in these time frames. And obviously, again, this is an aqueous experiment. Performance in the field is going to be different for a number of factors. It could be more advantageous, but certainly it would probably take a little bit longer. But again, this is just an evaluation of showing that this isn't just absorption, this is degradation as well. So in that same vein, how else can we prove treatment, especially if we're in the field post-injection? We can do mass balance experiments. If we have the ability to even go out and get samples. We can do long-term monitoring of groundwater, which obviously isn't evaluating the soil fraction, but watching groundwater data over longer periods of time can kind of show us what is going on performance from a performance aspect in the subsurface. And at some sites, some of our clients have even utilized CSIA. If that type of analysis is applicable to you, we can talk about that offline. We can also put you in touch with some of our partners in that realm that work with this on a routine basis. On the right there, this snapshot is from a site in Europe. And the reason I like this is when we go through our designs and we're asking you for pieces of data necessary to come up with an appropriate design for your site, we're going to look at historical groundwater highs. Do we have a smear zone? Where's our mass tied up? Maybe we go through the RDC and we identify specific zones where contamination resides. Well, here, if you look at that blue line at this site, that's our baseline concentration. So from roughly 7.5 to 10, this is actually meters, BGS here, you can see that's our smear zone. And then the lower lobe there on this graph is representing our dissolve phase at this site into the first zone of impact. Post-injection, we come back almost a little more than 3 years later. And you can see we've walked back the concentrations of soil mass in that smear zone. And this again is why we inject into the smear zones, because as groundwater washes into that cavity, we're going to get transport, we're going to get desorption and thus treatment. You can see here over a number of months and then thus years, we continually get that line walked back and we're achieving treatment. In the lower lobe there, as we would expect, the dissolve phase, the continuously saturated component here at the site, that is treated both relatively immediately and then with long-term control. This is from that same site. This is a source zone well, MW01C. And the reason I'm including this is we get asked about how this process works, how we can monitor that in the field. Also, can we handle significant concentrations of LNAPL? This first portion of the site here, where's my pointer? Here we go. This first portion of the site here is where we did our 2-week pilot test, and then over here is our full-scale implementation. The pilot test did take place here around MW01C. What we see here in this pilot test is significant amounts of LNAPL that exist at this site. They do have a mechanical system running. Even still, they do get some fluctuation in LNAPL thickness here. So we do want to work on reducing that. When the pilot test finishes, you see because of carbon capacity, we've got that LNAPL sorbed onto the activated carbon platform here. And then what we see are these rolling concentrations. You know, we would consider this process regeneration. This would be, you know, in another technology, this would be rebound. I don't personally consider this rebound here because this is a process in and of itself. This is that continuous transport of mass off of the soil onto the activated carbon and thus treatment. So every time we see these blips here, we've got treatment capacity available on the activated carbon, and thus we can absorb more, we can transport more off the soil column. Oh, I forgot I had a little animation here. So this just kind of reinforces what we did around this well for a pilot test prior to full scale. All right, so one of the last things I want to touch on here is other, less common contaminants we might deal with at a site, or at least contaminants that might not always be an injection goal for some of these BOSS 200 sites. As much as we would like, things don't always go as planned in the field. I think MTB is one of those curveballs that with almost any technology, you can see some of that. What we have here in this graph is a project site here where we did some injections. And what I'm going to call out here is our DPE2 location. We see that there is some absorption going on, but then some of those concentrations increase. And what we realized, this is one of the first sites where we had to do significant monitoring for MTBE. What we're realizing here is a preferential absorption, where we've got mass and where we don't have mass. So we don't have terribly much mass, especially BTEX range here in our other monitoring wells, our DPE points here, but DPE2 actually has a good bit of TPH. And that's one of the reasons here that we see some of this concentration kind of flatline and then spike. We don't, we got sequential treatment here, but we're also competing for absorption sites on that activated carbon. So we've got to blow through all the BTEX. We got to get rid of all that before we can start absorbing some of these contaminants of concern that have lower affinities for the carbon isotherm. And what we're dealing with here is something that this situation was not a criteria at the site, but the way we remedy this, if this was a criteria site, is to evaluate additional activated carbon, or again, as we mentioned earlier, a 2-step process. How do we manage that MTBE? We know we're going to get to the BTEX range. We know we're going to get to our TPH, a lot of it. How do we manage something like MTBE, maybe some of our other alcohols, TBA, et cetera? And the last thing I'll touch on before we get to a brief look at the RDC is we get asked a lot the differences between granular, powdered, liquid, or colloidal activated carbon. And again, this comes back to the performance of carbon on not just an isotherm basis, but a parent material and a weight basis. Again, compare products on a weight basis because volumes can be adjusted typically in our market using water or other additives. Here's a site actually up in Canada where there were multiple liquid activated carbon injections and then even an oxidant injection as well. And there's just not enough capacity. There was not an RDC associated with this. There was not evaluation of TEAs or microbial data for the site that we could see or our client could see. So we were asked to step in and remedy that. And a lot of this in the RDC phase was just based upon carbon capacity. If they had had enough carbon capacity, they might have seen better results. As you can see, when we stepped out with the trap and treat injection, we certainly did that. So briefly, looking at an RDC, I'm not going to focus too much on this, but the way we go about our projects, specifically focusing on BOSS 200, is we want to look at where our contaminant mass is distributed, both vertically and horizontally. We get a lot of projects where we have limited soil data, old soil data, maybe the portfolio or the project shifted between consultants or multiple consultants over a number of years. Long well screens, problematic. We do see designs that are blanket approaches when we don't really need one. This example here, this 3D model on the left is from a site in the US where we were dealing with chlorinated solvents. And what we're looking at here is each of those bore strings has a green dot on it. That's an RDC point. And those RDC points essentially make up the entire area that was proposed by another technology provider working with another consultant. And that was solely based on groundwater data. And you can see when you go look in and you find the pockets via soil sampling, high density soil sampling, that you can derive where the mass is that's contributing to the groundwater issues you have. And so this is our model of the site. You can see a number of these lobes are actually pretty shallow. Some of them are deeper. But again, the client saved a lot of money by not blanketing this whole area with reagents, or possibly repeated blanketing with reagents. We talked about some of this detail when we do an RDC process. We're typically doing these somewhere between 20, 25, 30 foot centers across your site. They are usually every 1 to 2 feet from the smear zone down to the bottom extent of our targeted zone. We could also get asked a lot, do you use high resolution site characterization tools, HRSC? The overarching comment there is they are a tool. A tool is a tool. And they're very useful when you don't know a lot about your site and you maybe have a large plume or a dilute plume, or you're searching, for source. Typically, when we have an idea of what we're dealing with at a site, that's where we move over to the RDC process. We want quantitative data. We don't want qualitative data. I can't take an electrical output signal and tell you exactly how much BTEX you have there from it. So we want to move into the laboratory analysis. So this is where we utilize RPI's lab. We'll take samples that either your crew or our crew generates in the field through the RDC process. RPI will run them pro bono, and that will allow us to update your CSM, and then we'll come up with a design based upon that CSM. If you have further interest in this, again, these slides will be available to you if you reach out to Bob Elliott. There's also an ITRC guidance document that details a lot of this. And one of the things in this RDC process I cannot hammer home enough is soil mass is critical. So how do these get applied briefly? Our overburden projects are top down using direct push technologies and a specific injection rig. Similar with pre-drill, this is something where we would either use sonic or hollow stem or solid stem augers to achieve depth. We'd backfill with hydrated bentonite, and then we could probe right through it, treat it just like a direct push site. That's a pre-drill is applicable for transition zone, weathered bedrock, glacial till, anywhere where we can't probe very easily. And then in bedrock, obviously we're going to use injection wells. These are going to be uncased because we're going to use a straddle packer setup with an 18-inch interval to succinctly inject on each of the fractures or features we're interested in. And we do that bottom up. You always want to work bottom up out of a well for injections in case you have integrity issues with the borehole or other jamming that can occur when you're tripping down instead of tripping out during injection. Here's a picture of our straddle packers there. You can see Ray's calling out that 18-inch interval. And here's a trench application as well. So conventionally all iron, we can work with you if it's shallow enough to use that. We definitely recommend going for it. No point in trying to make it too complicated. So briefly, I wanted to focus on 2 project summaries. This one's actually a pre-drill example using BOSS 200. You can see an extensive array of technologies were applied over the years. That's not to say any of these assumptions were wrong based upon technology, but it comes back again to doing an RDC process, knowing what our soil mass is. So here's a little look at that site. This is in the Northeast. It's an interstate rest stop. And we're talking about both construction debris. There's shot rock from the construction of the turnpike. There's also a glacial till setting. There's also some fill material as well used in various points along this interstate, possibly here as well. Most of this site, though, is underlain by shot rock that was placed during construction. When they built the rest stop, they also built the tank cavity directly into that shot rock. So we've got tanks lying on a very coarse material that's not easily probed. It's also very hard to categorize what mass actually resides at what intervals. What we did here after completing an RDC, we looked at doing a pre-drill technique to get through that. So each one of these points in this PRB that are pre-drilled are bentonite columns within the subsurface that we could probe through with 6-7 series rig or better. It's actually even easier than probing in most overburden settings. And then the injection actually propagates away from each of those columns when we do an injection interval. It cuts through this like a hot knife through butter. And because of the pressures we inject at, we're not carrying bentonite with us. It literally parts the bentonite column and out into the formation. And here's some of the results from that PRB, our up gradient there in dark blue and our down gradient in orange. And you can see here a challenging site with the fill material using the unique pre-drill technique. We were still able to implement what would be a fairly typical BOSS 200 PRB in any setting, obviously in a little more challenging setting here. And we're getting the results we need, protective of an offsite diurnal stream, seeps, a wetland area that lies just to the north of the site. And my last example here, I always like to include this. I don't want people to think that most of our sites are extremely large, which they can be, but this also works even on small sites, postage stamp sites, corner lots, Y lots. We get a lot of those here in the mid-Atlantic where I am. So this is a gas station example. This one's on the West Coast. Typical historical mechanical extraction system functioning to reduce concentrations. They're getting diminishing returns. The original design here was to actually blanket about 5 to 14 or 15 feet below ground surface within the area defined by a lot of these PB points, which actually we put in for an RDC. I'll talk about that in a second. But blanket a lot of that northeast corner there of this lot that you see with another reagent. Again, that was predicated upon limited soil data using existing monitoring wells at the site and a few extraction wells. Soil mass not really considered here. And what we're dealing with is a silty sand, sandy silt. So we should see good results with reagents, but you've got to know where to put them. So those PB points 1 through 5, that's our RDC process. We got those samples back. This graph on the right here, you can see that most of the mass at this site is in the bottom layer of that silty sand. It's riding on top of weathered granite. It's also into some of the weathered granite as well. So we've got this nice 2 or 3 foot layer right there at the transition zone at this site where we need to target. And that's what we did. This design is targeted to that zone. We also broke that vertical profile up into 3 unique areas on site. Again, this goes back to that RDC process. We want to know where the mass is. We want to know where the reagent needs to go. And in doing those 2 assessments, we can decide how much product has to go and where. And you can see between the shallow and deep zones here, we've got a different loading per interval. And this isn't just to do this right. This is also a cost savings for your client. This is not a blanketed approach. And you can see some of the other things we called out here. We did add some additional gypsum here. We did have a slightly higher TEA demand. And then we also couple all this up again, BOSS, gypsum, bacteria. Those ratios have to be succinct to allow this whole process to work, all determined by the RDC process. So here's the results from this site. We're looking at benzene and TVPH. You can see immediately post-injection, significant drops of, again, the power of activated carbon absorption. And then we're talking about long-term treatment. We can show that here. But we also see here in MW1, we can also see that there was a good bit of mass there around MW1. So this was that regenerative process that I mentioned in earlier slides. And here's what our ISO contours look like here. This is benzene. We had a 15 ppb standard to meet here. Within 4 quarters, our 2 primary monitoring wells, MW1, MW3, were under that standard. Obviously, there's some places in this country where the standard for benzene would be lower. I get asked a lot when I show this slide, how many more quarters or months would have taken. I can't answer that. It's site specific, but when you see this type of performance dropping 7,000 ppb down into the tens, single digit range, you can certainly see there's capacity and performance here with this design and installation. And that's where I'll end the Boss 200 presentation for today. I've got Bill Brab, my colleague from Kentucky. He's been monitoring the questions and chat here. And Bill, if you want to unmute and let me know what we've got, how we did, where we want to go for discussion, I appreciate it.
Yeah, no problem, Derek. Am I coming through audio okay?
You're great. Sounds good.
Excellent. Great presentation as always. Thanks to everyone for taking the time today to hear the RPI presentation here and sticking around with us here for the question and answer session. We do have several questions in the chat, and we can start with those in order here. The first question relates to the Boss 200 slurry when mixed up. We have a question about TDS, which I would translate as being slurry density. Can you talk a little bit about the slurry density and how it relates to an installation in situ?
Sure, and that's a great question. So we didn't touch on it earlier. It's a bit of a deeper dive, but Boss 200, because it starts as a powdered activated carbon, has a lot of versatility when it comes to the type of slurry, the density, the ratios we can mix up to do some of these installations. So I would say typically, while it's driven by the contaminant concentration, the geology, are we limited by how much we can put in on either of those parameters? That's one place to start. But we do have a fairly wide operating range that Boss 200 allows because it is powdered activated carbon. We could see a 4-to-1 ratio all the way down to a 1-to-1 ratio in terms of product pounds per gallon. In terms of slurry density, we don't typically specify a specific density for it in a design. We can extrapolate it out from the pounds of product, from the volume of water we're using in that mix. If we are doing a very heavy, if we have a very dense or viscous slurry mix proposed for a site, that's maybe at the upper limits of what we believe the geology could take. Excuse me. We may advise of a pilot if there's, if it may not make sense at a very small site, but certainly at most sites, a pilot would be a good way to go about evaluating the ability and distribution of that design to be utilized at a site. Similarly, at the other end of that spectrum, because this is a contact sport, there is a lower limit of operation for some of these products as well from a density standpoint. You typically don't want to go too much past 1 pound per gallon with the slurry, because we do want to make sure we're not just getting the right amount in based upon the calculations from the RDC and the SPCA data, but we want to make sure that we have enough to actually make contact. You could say if I have a couple ppb of a contaminant in there, I'm not going to need a lot of carbon, but I also need to make sure when I'm injecting and co-mixing these in situ that I have enough product to actually reach where that contaminant is. So while on paper it may not be a lot of carbon, the concentration of carbon in that mix may actually be bumped up because we're trying to achieve contact and distribution in the subsurface.
All right, and I think that answers that question. If not, we can follow up offline with that separately after the webinar is over. Have another detailed question here, specifically related to PFAS and chlorinated solvents or light solvents. And I know you touched on the PFAS discussion earlier, and just to circle back to that, the question here pertains to having a commingled plume where it looks like the dominant contaminant is going to be PFAS with some light solvents. Can you go over and just reiterate the stance on the PFAS presence in relation to other contaminants?
Sure. And this certainly may be better with this question to follow up with this person a little bit more offsite, but as a general overarching comment to this question, again, we're not going to involve RPI products at a site that has PFAS, PFOA. From a injection standpoint, we've been approached, AST has, because of our bedrock truck and some of our other capabilities. We've been asked to implement other technologies that are tilted towards that, typically evaluated on a site-by-site basis. But if we're dealing with, a preponderance at a site of PFAS, PFOA, any of the perfluorinated compounds, not my area of specialty, so I can't name too many more, but that's something that we would probably only be considering if the client selected another injection or another product for those for injection, but we're not going to use RPI products for that because we don't have a treatment mechanism. I know some consultants, some regulatory bodies, even the Army Corps and some other entities are using activated carbon in these capacities. That's something that's you're interested in using another technology outside of our realm that needs to be injected, you could reach out to AST offline and we could discuss that. But again, these technologies we discussed here and also last week for the chlorinated solvents, not something that we're going to use trap and treat technologies for.
All right, thank you. We can follow up with that person offline to talk about that in more detail once the webinar is completed. Yes, and that got an answer here that looks like it clears it up, but we'll still follow up offline if there's any other discussion on that. Have somebody here who looks like they're in California and wanting to know if we're approved in California and our current status with the water boards there to do work in that state.
Sure, great question. Thankfully, due to some efforts of my colleagues on the West Coast and in Kentucky, currently the only water board that we're still pending approval in is Santa Ana. The other water boards we are approved for use, which certainly helps open up that market for us. We've done a number of designs out there already. We do expect one or two of those projects to post in 2021. The gas station project I showed you a couple slides ago, the final project summary example, is actually a site outside of the San Diego area. So that was one that we did execute in California. We are excited to learn, hopefully in coming quarters, if the Santa Ana Water Board will approve this technology. We believe they will. All the other water boards did. But that's really the only outstanding locale that we don't have approval yet in California.
All right. It looks like there's a question that popped in here prompted by the previous question about PFAS and light solvents. So can you talk a little bit about commingled plumes where you may have a situation with petroleum hydrocarbon with some sort of chlorinated solvent? Give a little bit of discussion about that.
Sure. Great question. We're not always limited by dealing with one or two contaminants, right? So when they bridge the spectrum between especially petroleum hydrocarbons and chlorinated solvents, a lot of our evaluation, again, going back to an RDC process here, we need to evaluate what has the higher demand on the system from either a CVOC or a petroleum hydrocarbon standpoint. The facultative blend of bacteria that I discussed today, a different but appropriate blend for chlorinated solvents that my colleague Mike discussed on last week's webinar, which again is available on the Trap and Treat website. We've been recording all these for posterity. We're going to look at the demand and decide which requires not just different, the carbon demand is one aspect of this, but what blend of bacteria and at what ratios are we going to require? We also have to determine, a lot of times in a commingled plume, there could be issues with pH, alkalinity. Certainly, are you in a reducing environment? Are you in a heavily oxidized environment? What are your site constraints? Because CVOCs and petroleum hydrocarbons don't have a lot of the same treatment pathways. So really, we're trying to find a way to access those contaminants by drawing them onto the carbon and then using typically a biological process to break them down if you've got a commingled plume. So again, that's a very site-specific question. It is something that we can handle though, and we would obviously, if you've got one of those here on this webinar, we'd certainly love to evaluate it with you to decide if it's a fit. One thing I should have mentioned sooner in this presentation is some of this evaluation process, whether it's real rudimentary, from looking at information that's available now, or even as we go through the RDC process, or even maybe a pilot, if we get to a juncture where this isn't a fit, that's something that we will let you know as well. Certainly, we don't want to, put the proverbial square peg in a round hole, if we don't want to underperform. So if we don't think this is the right fit, we're not going to, continue down that path with you. That doesn't serve any of the entities involved. It's not something that we've ever done at the group, and I think it's one of the things that we pride ourselves on. And quite frankly, it was one of the reasons I actually joined AST, was because of this, the ethical process that we use when we do an RDC and do these evaluations. I think everything we recommend is appropriate from a technology standpoint, and we'll tell you if it's not, and try and help you find another alternative.
Right. Thank you, Derek. I have another question populated here during discussion, specific to changes to the aquifer itself, specifically groundwater flow direction. Have we seen any instances of that?
Off the top of my head on my projects, I don't recall post-injection seeing a shift in groundwater flow. Again, there is a lot of poor structure to these products. So while we've talked about these being slurries, once they're injected in situ, or even, and we'll get into this more in the bedrock presentations in December, even if it's injected into a fracture, it's not like we're injecting a very fine, say, clay-based material, like think bentonite, for example. The poor structure, the porosity of the carbon allows flow through it. So I'm sure if you had a way to measure very minute changes in groundwater flow velocity, you could probably pick up on a little bit. I'd have to, obviously you're filling a fracture or a lens or something with some material, there might be some change, but we haven't seen a significant change in groundwater velocity or flow direction post-treatment that I can imagine, at least at my end. I don't know, Bill, maybe anything you've seen in your projects?
Yeah, I was going to follow up to that as well from my perspective that I have not seen a significant shift in groundwater flow direction or a change in aquifer characteristics. Just like you said, the particle size is not so significant that it alters the matrix itself. And when I know you talked about slurry density earlier and about how much is going into the subsurface, but when you look at a mass per unit volume scenario, the typical installation on these facilities is going to be, below 0.5 pounds per cubic foot of material. So it's a relatively insignificant amount of material in the grand scheme of the total aquifer matrix itself. We're not altering it substantially enough to cause that significant of a change. So that would be my stance. And I have not seen on the sites that I've worked on any significant shift or anything that would suggest that that's caused by the injection or the installation itself, but would rather be just the standard variability that you would see throughout the fluctuations of the year.
Mm-hmm. And I think just to piggyback on that, Bill, especially when you're in sands and we're doing radial co-mixing in our injections, we didn't focus too much on this in this presentation, but when you're in coarser unit material, we actually increase the pressures, maybe contrary to some beliefs. And the reason we do that is because we're going to co-mix it with the formation around it. So like a high energy beach wave that's tumbling the material with the formation, we do get it evenly distributed into the matrix. So we don't have these plugs, these very high density lenses when we're done in sand. That would be detrimental. On the flip side, if you're in a finer grain material, certainly you're injecting lenses into, say, a clay or a very fine silt or silty clay. You're going to get these areas where it is a 3D feature, but it's mostly planar, it's mostly 2D. So there is some insertion within that. But again, our goal there is, in a clay, we're not looking to, I haven't seen an effect on flow direction or flow velocity, but that coarser, ever so slightly coarser area, that lens we're putting in does allow for both advective capture and additional transport off of the, in this case, clay in my example. So there is some benefit there, but to say we've seen an overall change in direction or velocity, I've never seen that. But it's a good question. I know there's other technologies out there that might be dense enough if they're, depending on how they're installed, that may have that issue. You know, I would say if you're using maybe a conventional or commodity-based activated carbon or maybe other ground mineral reagent, you could certainly have that concern. You'd get lower pressures, which a lot of the other injection techniques use. You would get formational straining at the tip, clogging, if you will. So that I could see that plugging up the formation. But in the way that we inject these in the RPI group, we don't get formational straining, so I don't see that as an issue.
All right, thank you for that clarification. Want to be conscious of the remaining time. We're rapidly approaching the hour here.
Bill, did we lose you, or did you lose me? Bill, I think we lost you. Okay, Ed, you can still hear me? Okay, so I think.
Back.
Oh, there you go, Bill. Sorry, everybody.
Sorry about that. I don't know what happened there. Did you get the question, Derek?
No, I think you know, we can address some specific questions offline. As I think you were about to say, in the interest of time, during that hiccup there, I did open up the chat and the questions. There are a few here that you or me can reach out to these people specifically. One thing I did want to note there, I did see a question about injecting around tanks. There's another one about injecting around utilities. I think the overarching comment to that, and we can be more specific if people want to reach out to us on this, is you know, determining in your design the locations that these injection points are going to be laid out in the field. Certainly, a utility, an active tank pit presents a potential preferential pathway or conduit, so we want to be away from those. I think the best way for me to describe the layout in the field off of our designs in the lab or in the office is when you're talking about the way we inject a specific density of slurry, a specific volume, slurry shot volume going into the subsurface, we have pretty decent idea of control and propagation from where they would go. So shot shaping may be a bit of an overreach because that would imply some control, but we have a decent idea of how these are going to propagate in the subsurface. And typically, if we're on a very active site with lots of utilities, we would certainly, if we haven't done a pilot already, our first few injections would help us kind of work through and realize what the actual distribution on that site is. So as we move into more congested areas with subsurface features, anthropogenic features, that we could be cognizant of those and stay away from those. Now, there might be instances where we know there's product tied up along those cavities, and that's something that we would address with each, you know, project manager individually on how we're going to work around that. Most cases, you know, we just did a site here in New Jersey last week where we knew on 5-foot injection centers that we could distribute product within 6 to 12 inches around a lot of the tank cavity there. And we know that this will have some advective capture to it. We know we've got preferential adsorption versus the soil fraction. So we will get transport out of those cavities along those utilities at that site without being right up on them. And certainly too, from a safety standpoint, we don't want to be up on them with the drilling component. Certainly we don't want to be up on those features, those utilities, because they will be preferential pathways and the product won't reside where we want it if we intersect them. So Something we'll work on each project to do, both pre and you know, in the design phase and before we head to the field, and then once we're in the field, laying the project out. So we've run a little bit long in the Q&A. I do apologize and thank everybody for your time. If you have any other questions, again, my email, Bob's email is on the screen. You can also go to trapandtreat.com or astenv.com and reach any of our owners, project managers, senior project managers, and we can help you with your site. That's all. I hope everyone has a great Thanksgiving holiday next week, and I hope 2020, you know, we obviously hope we have a better 2021, but I hope your 2020 finishes well for you and your company. And thank you very much for your time.